All right, well, we'll get started. Welcome everyone to an OpenTEAM in-depth webinar. We have a good team from the Regen Network here today. And just to open it up, this is really meant to help build the knowledge base of the OpenTEAM community in a way that fosters coherence and collaboration so we can better serve our growing and diverse membership. So through this today, we'll illustrate and document the dynamic nature of our community, inspire and share new concepts and technologies. And I think a few weeks ago, there was demand for kind of an overview of Remote Sensing 101, which will also be kind of presented today. So we have three presenters from Regen Network: Sam Bennetts, Gisel Booman, and Sophia Leiker, all from the science team. So I'll turn it over to the three of you. We'll have up to 30 to 45 minutes of a presentation and the rest for questions and answers. So we'll have some time for interaction as well. I see your screen.
Perfect.
You should be ready to go. Thanks again for being here and presenting today.
Great, wonderful. Yeah, so as Laura said, thank you all so much for joining. My name's Sophia. I'm from the Regen Network science team. We're really excited to really dive into some of the great work we've been doing over the past year, specifically looking at kind of the benefits of remote sensing, why we're using remote sensing, and then taking a deep dive into our remote sensing methods for measuring soil organic carbon. So to start us off, I'll do a quick overview on what we're going to cover today. As Laura mentioned, I know there's a wide range of people who are joining us and who may have more background on remote sensing. Some of you may never have heard of remote sensing. So first, I'm going to do a little bit of a background on what is remote sensing, why are we using it, some of the benefits of remote sensing, and then I'll be passing it off to Sam, who will be presenting our actual Grasslands methodology, and then a case study where we actually use this methodology to quantify soil organic carbon in a farm in Australia over in New South Wales. And like Laura mentioned, we'll open the floor at the end for questions, and these may be about remote sensing if you have questions for us specifically on different satellites or remote sensing background, or if you have questions on our methodology itself. So we should have plenty of time for questions at the end, so make sure you save any questions you have for us, and we can kind of have a more open discussion. So to dive right in on what is remote sensing, I figured I would start it off with just a quote from the USGS. And they define remote sensing as the process of detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation at a distance, typically from satellite or aircraft. And special cameras collect remotely sensed images, which help researchers sense things about the Earth. And this may all sound really complicated, but ultimately, the goal with remote sensing is looking at the physical characteristics of Earth from afar. And you can collect remote sensing data from a wide variety of tools. So you can gather remote sensing data from drones, you can gather remote sensing data from airplanes or helicopters. But really today, what we will be focusing on and our kind of approach to remote sensing is using data collected by low Earth orbit satellites such as Sentinel-2, which Sam will touch on a little bit later. So there's a lot of, I won't get into all the details on the advantages and disadvantages to each of these, but just know that there's a lot of remote sensing beyond just the satellites we'll be talking about today. So kind of to dive right into some of the technical background around remote sensing, specifically when we talk about remote sensing using satellite imagery, is there's two main metrics that we'll often talk about and that Sam will talk about when we get into the actual meat of the methodology. And the first is spatial resolution. And when we're talking about spatial resolution, really what we're talking about is the size of a pixel. And you can kind of think about this as different levels of photographs. So you can have an image from a high resolution camera, really expensive, like multi-$1,000 Canon camera, for example. And you know that those pictures that you get from a really high resolution camera are going to be very detailed. When you zoom in, you'll be able to see a lot of the detail within the image versus maybe a lower resolution camera like your iPhone or something, which might have a little bit more of a coarser resolution, and when you zoom in, it might get a little blurry. So the same thing applies when we're talking about spatial resolution of satellite imagery. So satellite imagery can range in spatial resolution. We often talking about it in the units of meters, but it can range from like 250 meters all the way down to 1 meter or even sub 1 meter. And you can see down here in this little bottom infographic how that reflects the output, the pixel output display. So you can see that as you decrease the pixel size, you're actually able to more accurately reflect what's happening on the landscape. So at the 1 meter scale, you really can see in detail what's going on in the landscape, but when you move up, more to the 30 meters, it's a little bit more coarse resolution. So again, we'll talk about when talking about remote sensing, you'll often hear the term spatial resolution. And really what we're talking about there is just the size of the pixel. So that's the first metric that's often used. And the second metric is temporal resolution. And essentially what temporal resolution is just the time between images. So again, thinking about as we are gathering images from satellites which circle the Earth, it's going to take a certain amount of time for the satellite to take a snapshot of a certain location, such as say San Francisco, and then circle the Earth and revisit to that same place where it can take a snapshot of the same place. And so again, this is just when we talk about temporal resolution, it's about this revisit time between when you're gathering images. And the revisit time can range from say 5 days for a certain location on the globe to up to 10 or 20 days. So again, when we're talking about satellite imagery, really the two metrics that are used are spatial resolution, and then the second is temporal resolution. And then moving over to the right, again, this is a really basic breakdown of remote sensing, but I think it's important to touch on the fact of what we're talking about when we talk about spectral bands. So when we talk about the different satellites we use, we'll often talk about the number of spectral bands they collect. And essentially, spectral bands just align with different ranges within the electromagnetic spectrum. So you can see on the top is just basic breakdown of the electromagnetic spectrum. And as we all know, there's a certain range which encompasses visible light. And within that visible light, you can break the wavelengths into different ranges which are collected by a satellite. So satellites often collect bands in the red and the blue and the green visible light spectrum. But the cool thing about these satellites is they're also collecting images or snapshots outside of the visible light spectrum. So you're not just seeing the normal picture coming in with the red, green, and blue band, but you're also getting information from bands outside of the visible light spectrum, such as from near infrared or shortwave infrared. So when you get all this information from these satellites, really what you get is a stack of different pictures encompassing different bands. So you have a picture of the red band, you'll have a picture of the shortwave infrared or the blue band. So when we talk about spectral bands, really we're just talking about these different snapshots which align with different ranges within the electromagnetic spectrum. So that's just the basic breakdown of the kind of technical background and details when it comes to remote sensing. So moving forward, in terms of what can remote sensing tell us? So not only do we have these bands, like I mentioned in the last slide, you can actually combine these bands to create and calculate indices. And these can tell us about a range of different information on the actual ecosystem health. So I'm just going to explain one, which is probably the most famous one, which is NDVI, the Normalized Difference Vegetation Index. And this is just a metric or a measurement of vegetation health. So on the left, you can see that healthy vegetation, when you're looking at different reflectance of the bands, it's reflecting about 50% of the near infrared band, but reflecting only about 8% of the red band. But then on the right, when you're looking at more of a stressed piece of vegetation or an unhealthy plant, it's reflecting about 40% of that near infrared band and 30% of the red band. And essentially what you do is you can combine all this information into this NDVI equation and get a final output metric, which will move you over to the right side of the screen where you can see that, all right, if you get an NDVI value of say 0.66 to 1, you usually can assume that the vegetation, whether it be trees or crops, are fairly healthy. But if you get a metric that's around 0 to like 0.33, you usually can consider it somewhat of an unhealthy plant. And I think Indices, I bring up indices because not only do we use indices, as Sam will touch on within our methodology for tracking soil organic carbon, but we also use it for some ecosystem health analyses. So this is just NDVI. I listed a couple other indicators you can detect with various remote sensing indices below, such as looking at fire impacted areas or the water content held in vegetation. You can also use indices to look at bare soil presence within an ecosystem or even look at the health of overall forest. So again, indices are just another way you can use remote sensing data to assess what's happening on the surface of the earth. And then from here, I wanted to touch a little bit on some examples of what can you use remote sensing for, why is it used, what are some of the benefits of it. So first, you can use remote sensing to map land cover across an area. And on the right, you can see just a Landsat image, and Landsat's a NASA satellite, but it's an image of a river. And you can use remote sensing and classification algorithms to actually determine a classification of what's happening. So using that image that you gather from the satellite, you can then use algorithms to determine, all right, these pixels align to pixels with water versus, the brown is indicating barren soil. So you can use classification algorithms to map land cover across an area as one of the ways you can use remote sensing, but you can also use satellite remote sensing to monitor, say, the rate of wildfire spread or map the structure of forest to understand overall forest health. I think in terms of OpenTEAM, and a lot of people on this call may be interested of, how do you use satellite remote sensing for assessing the health of crops within your fields, or even monitoring the change of surface water. So again, there's a whole slew of other examples on how you can use remote sensing, but these are just a few to kind of understand the different ways you can use remote sensing data in overall analysis. And then moving on, some of the benefits of remote sensing is remote sensing provides tools to monitor landscapes at a variety of scales. Again, going back to the whole idea of the resolution or the pixel size, you can use really high resolution data to monitor, say, an area of a couple acres, or you can use satellites that have higher or more coarse resolution to even map like land cover across an entire state, for example. So again, remote sensing can be used at a wide variety of scales. And also one of the main benefits is there's a lot of free and open source databases that have remote sensing data. So Landsat on the right, that's a NASA derived remote sensing data set, but also ESA, or the European Space Agency, has a lot of data sets in terms of what we use, but also even the USDA has remote sensing databases that are high resolution for the United States. So again, all these open source databases have resolution that are high enough quality that are fairly good to be able to assess the health at the overall field scale. And then finally, before we really dig into our methods, I wanted to touch on one of the largest benefits, at least I believe, in terms of why we use remote sensing, and that is using remote sensing for time series assessments. So I really love this infographic on the right because I think it really encompasses the strength of why we can use remote sensing to track change over time. So you can see that it looks like they're pulling out a certain portion of an image from, say, Washington, and you have a certain image from a certain date. And then from there, because these satellites have been circling the Earth and taking these snapshots over a period of time, you actually can compile a whole series of these snapshots or create like a stack of what we call images. And then within these images, you can even go down to a pixel level or even a certain portion if you want to look at a certain parcel within this image, and then track the change over time by looking at the spectral value aligned with that specific pixel or for that specific field scale. From there, you can take that and then look at the change of the spectral index over time to kind of track, what was happening in the landscape itself. So you can see that this certain image, they're saying they're tracking from 1984 to 2016, but you can see it around like 2002 or 2005, something happened, a change happened. And you can see that by looking at the actual pixel level, or the field level, that there is a drop in the spectral index. And so depending on what ecosystem type you're looking at or what was happening there, you could say, hey, this could have been a drop due to, if it's ecosystem health, say a wildfire, or did deforestation take place? All these things you can do to it, you can assess using remote sensing. So for us, when we use time series assessment for change over time, what we use these for is to look at the change in percent of soil organic carbon at the pixel level, and also look at the change of ecosystem health over time. So again, I hope that provided a little bit more background on remote sensing for those who may not have known as much about the benefits. But now I'll pass it on over to Sam, and he'll dig into our actual methodology for tracking soil organic carbon over time.
Sweet. Well, yeah, now that Sophia has given us an overview of remote sensing and how it can be used, Gisel, Sophia, and I wanted to share some of the work that the science team has been doing. So for the last year, Gisel, Sophia, and I have been working on a methodology to measure greenhouse gas reduction in Cobenefits and grazing systems. More specifically, our methodology is a remote sensing approach to measure carbon sequestration and identify or quantify soil organic carbon stocks at the field scale. And we're doing this for grasslands under the practice of prescribed grazing. So our methodology relies on multispectral satellite imagery with a spatial resolution of 20 meters or higher. And then we couple that with machine learning algorithms to kind of estimate soil organic carbon stocks across an area and look at those change over time, like Sophia just showed. This is an open source approach, and the idea with it is to minimize the sampling efforts and costs. So you can go to the next slide, Sophia. So this is an overview of our Grasslands methodology, and it can really be broken down into three main stages. So the first stage is soil sampling and stratification. The second stage is data preprocessing, where we incorporate remote sensing data. And then the third stage is modeling and soil organic carbon quantification, where we use that ground truth data and satellite imagery to estimate stocks across the farm and then ultimately look at change in time. So the first thing we would do when we adopt a new project is we evaluate the project area to assign soil sampling locations. This is a pretty important stage in the process. In more traditional methods, you might use exhaustive sampling, where one might take hundreds of samples across the farm. So that's going to represent the spatial variability of the soil because you're collecting so many soil samples. But with remote sensing, it's a little bit different. We're requesting fewer soil samples, so we want to make sure that those soil samples are pretty representative of the spatial variability of the soil. So during this process, we're going to perform what's called stratification, where we essentially divide the project area into different parcels or strata that will share similar soil characteristics. Here we might use variables such as elevation and topography, vegetation or above ground biomass, hydrologic differences, or pedologic variables such as soil type and percent silt, percent clay. And so taking all those variables, we'll kind of make this classification. And you can see here in the image on the left, how this project area has been divided into all these parcels. And so what we're assuming is that the soil type within those parcels is relatively similar. So it might share, similar topography, or it might, have a lot of vegetation in that area or a little bit, or the soil type is generally the same. So once we divide that, we'll randomly pick some of these strata and then assign soil sampling locations within that. So then the project manager or the land manager will go out and collect these soil samples at those assigned locations and then send those to a lab. And so at the lab, they're going to be testing for percent soil organic carbon and bulk density, which is used to measure soil organic carbon stocks. And then for the scope of our methodology, we're also assessing other soil health indicators such as pH, nitrogen, sulfur, a bunch of other variables. So once that's done, we'll go into this data preprocessing stage. So when they collect the soil samples, we also have them collect the soil sample location. And so the soil sample location is what ties the remote sensing data to the ground truth data. So the image in the middle shows, I think it's just a satellite image, and you have the soil sample location overlaid on top. And essentially what we're doing is we're taking our satellite image and our other remote sensing data, whether it's like a percent clay raster, or maybe an elevation like DEM, digital elevation model. And we're saying at that soil sample location, we're going to extract all that remote sensing data. And then we're going to turn it into this nice data set where we have our percent soil organic carbon and all of our predictor variables. So if you were to look at this in a table, you might have rows with your different soil sample locations, and then a column with percent soil organic carbon, and then each variable listed in a new column. So now that that data set is set up, we can go into the modeling. And this is where we're going to be finding correlations between the ground truth data and all these predictor variables to try to find correlations that we can use to predict percent soil organic carbon. There are a variety of ways to do this. Originally, we were using linear and power regression models. So in this case, we would take one variable, in this example, band 6, and then we would compare that to percent soil organic carbon to find a correlation. And if there was a correlation, we could use that to estimate soil organic carbon at unsampled locations. More recently, we've been using machine learning models such as random forest. And what's really nice about these is you can incorporate an entire data set into these predictions. So rather than looking at just a single variable, now that you can incorporate all these variables and identify correlations that might not be seen visually. And this is really powerful because incorporating like topographic data in a bunch of different bands has actually helped increase our accuracy and create better predictions. So Sophia, you can go to the next slide. Sweet. So this is kind of an example of how we go through this. On the left, we have our soil sample locations. And then, this first arrow, we've finally found our correlation with our machine learning algorithm. And then we're going to use that to predict soil organic carbon at unsampled locations. So the image in the middle shows this prediction. So we've masked out everything that's not grassland. So all the trees, roads, waterways have been masked out. And now this is just grassland, and it shows the spatial variability of soil organic carbon across the area. The darker red is higher percent soil organic carbon, and the more yellow is a lower amount. And what's really cool about this is you can see that for every 10 meters, like every pixel, we have a different prediction. Which is really cool because you're accounting for that spatial variability over a short area. Then we use the bulk density and the soil depth to estimate soil organic carbon stocks. And the image on the right shows like our final stock calculation. So you can see through all these parcels how the amount of stocks change and how much carbon has been sequestered. Get a next slide. And then finally, what we're going to do is we're going to compare we're going to perform this time series analysis where we're comparing 2 years. So we have 2019 on the left and then 2017 on the right. And you can see some of these parcels have gotten darker, and that's representing that more carbon has been sequestered in that time period, which is really cool. And then to calculate our final creditable carbon change, we're also going to take into account the animal emissions and the model uncertainty. So we have had pretty good results with our predictions so far, but there is a certain amount of uncertainty associated with estimating percent soil organic carbon in these machine learning algorithms and calculating bulk density. So we want to make sure that we take all that into account in our final kind of carbon stock quantification. Just a few more notes. I think you can go to the next one, Sophia. So the image type that we've been, or the satellite image that we've been using most frequently is Sentinel-2. We use this mostly because it has a high spatial resolution. So it has that, it says 10 to 60 meters, but it's really 10 to 20 meter spatial resolution. So we can have predictions every 10 to 20 meters. It also has a pretty good revisit time every 5 days, but we usually get an image at least once a month. You can go to the next slide. And this is just kind of a slide to show how spatial resolution, how important it is. So on the bottom, you have Landsat, and that has a spatial resolution of 30 meters. And you can see that it's more granular. And so you're getting pretty good predictions, and you can see the spatial variability. But the image on top, Sentinel, with 10-meter resolution, is just a little bit more granular. So you can have slightly better predictions. Finally, I guess another application that we've been using remote sensing for within our methodology is assessing co-benefits. So one of the co-benefits that we look at is kind of the ecosystem resilience in vigor. And what we're doing is we're comparing the project area to the landscape surrounding it to see if the regenerative practices go beyond carbon sequestration. The image on the left shows a land cover classification I did. So the blue represents water, the dark green is forest or kind of heavily vegetated areas. The light green is grassland, and then the red and brown are man-made objects and roads. And what we did is we chopped out the project boundary, and we're looking at the NDVI or vegetation health within the project boundary, and then comparing it to the surrounding landscape. We're also doing that for bare soil index. So we're just seeing the amount of bare soil exposed and seeing if over time, beyond carbon sequestration, we're seeing, more solid soil. And yeah, so with that, I guess we will open it up to questions, and I would invite questions pertaining to remote sensing, what it is, kind of the basics, but then also to our methodology. So yeah, I think we can stop sharing and people can start asking away.
Well, first, I just want to thank Sophia and Sam for this. I think there's a lot of folks who are really looking for some of that basic remote sensing information. I thought maybe I'll kick off while folks are formulating questions around essentially your versioning process, because obviously these are evolving, and particularly from the OpenTEAM community, where a lot of this will be, we have hubs that are on the ground doing a lot of direct sampling. And so what are the kind of training data sets that would be most useful in terms of improving confidence in prediction in general? And this is sort of just both sort of in general from a remote sensing, but also sort of more specifically in terms of your own process.
Really just like lots of soil samples. The success of a lot of these machine learning algorithms, or really any regression technique, is just, the amount of data inputs that you have. The more data that you have, the more training, or the better trained the model can be and the better predictions you can have. So just having these larger training sets is really nice. So, if a farm were to provide a bunch of soil samples, or I think the long-term idea would be to regionally collect enough soil samples across, a state or something like that, that you could have a well-trained model that requires less input because you've, had so much training input. So yeah, if that answers your question.
Yeah, I mean, I guess the second part is sort of your versioning of this and sort of how you're incorporating new data sets or specific projects that or regions that you're targeting to sort of create those training data sets.
Yeah, so far we've only run this on just a few projects in Australia. But the idea is that we want to open this methodology up for anyone to use in any area. So I noticed a question in there if any of this was automated, which a lot of it is, and our code can be found on GitHub. So, I mean, whether you share that data with us or if you want to, use our methodology to kind of train a regional model or a field model specific to your area, those would both be great options. And yeah, in terms of versioning, I think just over time, collecting more data and just having that in the archive to better train these models that we're going to use.
Great. I see a question from Alden. Alden, do you want to comment here?
Sure. Great work, and don't take me wrong here, but of course in NORI we're trying to reconcile some of the big differences we're seeing between some of the estimates that come out of these new ways of doing things and the old-fashioned reference site sampling and process modeling way, which we know has large deficiencies. So we're trying to find a path, not be on one side versus the other. But when I've been, for other reasons, because I had to give a presentation to Australians yesterday, looking at the Zero Soils map for Australia, and the soil map you just showed suggests 2017 background soil organic carbon stocks that are much larger than suggested by the Australian government soils map. So I'm curious what you found. Are you saying that the Australian soils maps are just completely way off base? And because if they could be that much off base, then so could the American soils maps, or what are the other possible explanations for the really, really big differences between your map and their map that I'm not guessing?
Yeah, I can answer that. So first, I'm not sure where you got the 250 tons per hectare in the project. I will check, as I don't have that number in my mind right now. But what we saw is that we were like getting stocks within the normal ranges of the stocks that are supposed to be there for managed grazing. What we did find is a very high sequestration rate in those areas, which is related to the particular management that they do there, which is AMP grazing. It implies, high frequency of movements of animals for very controlled periods of time, and they pause the time that they revisit those parcels. And those management practices tend to increase the soil organic carbon sequestration by 10 times. So when you compare a regional map to this particular parcels, you might get like very high differences. I guess those maps are more regional scale than what we are creating, which is within the field scale.
Again, I didn't ask the question with the intent of putting you on the defense. Please understand that. I'll follow up, Giselle, and I'll just send you the link to the it's the CSIRO Australian government website,
yeah,
which is the map that I'm referencing there.
Okay, yes, for sure. Yeah, just I wanted to clarify that we checked the stocks and they were like within the normal ranges. So that's why maybe we are talking about different units or comparing different things.
Okay.
Great. Well, we had a number of questions in the chat. I'm thinking maybe Dan Kane, if we had a response from Gregory to that. I wonder if Sophia and Sam, if you wanted to pick up Dan's question, or Dan, if you'd like to frame it for them.
Yeah, Dan, could you frame that a little bit more? Because I actually couldn't access that paper.
Oh, shoot. Okay, I'll see if I can find a better link. Yeah, so this, in the Quick Carbon program, we ended up kind of doing some similar stuff too, and realized that as we gathered some more field data and sort of expanded our ability to do sort of ground truthing of remote sensing only models, and sort of not dissimilar to what you're doing, combining both digital soil maps and data from satellites. The accuracy of those models began to look worse as we started to get more and more data to test it against. And this is sort of like a critique I've seen elsewhere in remote sensing and ecological modeling literature, that if you're not kind of considerate about how you choose and place some of those ground truth samples, you may get an inflated sense of accuracy. So not to say that that remote sensing for estimation of a property like soil carbon isn't still useful, but that kind of the how you generate that test data set matters a lot to interpreting those RMSE values that you produce. So, and yeah, so I've been trying to take a deep dive myself on some of this literature and figure out, okay, how might this apply to the world of soil carbon? So was just eager to get your thoughts in that regard and hear how you're thinking about it.
Sam, I think that you might take that one because you have tested a lot of models, and we tested a lot of stuff trying to avoid that, any bias there. Mm-hmm.
Yeah, I don't know if I necessarily have like a clear, definitive answer to that. I think that we're still, the methodology is pretty nascent in the early stages of development. And so even using machine learning models was relatively new. I have played around with like a lot of just, how the test train split happened and how that might have affected the model. And I did notice that sometimes, depending on how you split the data, it would have way higher accuracy than it would otherwise. So I played around a bit with that, but I haven't actually dug into any of the literature that you're referring to. So it would honestly be great to just like get some of that from you and have us dig in, because I know that you're doing very parallel work. And
yeah, I'd love to.
It seems like you have a better idea on that than we do at this point. So
No, I'd love to work together on it. And maybe that's a good thing too within OpenTEAM to start thinking about, because it's just sort of something I've seen in parallel literature from other fields like forestry and stuff like that. So,
which is really interesting too, because I mean, this is being applied to so many other things beyond, soil carbon measurement, whether it's, forestry projects, and there's tons of monitoring services out there that are, claiming really high accuracies on these like really massive data sets, which could be totally valid, but it is like just a very new field. So
yeah, and I think the chief concern I've heard from folks on this is mostly how accurate that is, and how much you believe that accuracy number has a lot to say about the utility of these methods for change detection. And that, which is kind of a key point, but not to like certainly really useful at looking at patterns in space. But we really need to have confidence in that accuracy number to then translate it to the ability to detect change over time. So, but yeah, let's connect.
Yeah,
great. Well, and a great prompt in terms of one of the roles with our active working groups around discussing our links with hubs and creating training data sets for remote sensing. So, and along those lines, I want to go to Rob Trice and then Christoph, perhaps. But Rob, you were asking particularly about some of the management, sensitivity to management on the landscape, and that was certainly also part of this training data set. And what our hubs are interested in is, can we detect some of these, the different types of management practices and how those start to show up in change over time. But Rob, I'll let you frame it.
Yeah, exactly. Just kind of, if we start to think about A/B testing in different pastures, how can we look at applying different practices and the co-benefits of different practices applied to the same pastures? And do you have the ability to look at something like composting, or if I put a particular seed into a pasture, and so it's fundamentally for me, it's the ecosystem health. It's looking at the animals, it's looking at the practices, and then fourthly are the business concerns. Those are the four big data sets that we need, but we need to look at the correlation of all of those, particularly the first three, to figure out the optimized technical implementation of climate smart practices. So are you looking at, do you have the ability to look at things or capture that information? Like compost was applied in pasture 42, but not pasture 41, and that variability.
Yeah, I think that, I mean, that's not a project that we've necessarily worked on yet, but I don't think that would fall out of the limits of remote sensing, as a field. I think that the value of remote sensing is that you can use these data sets to look at spatial variability, and, you very well might be able to look at, different indicators and say, oh, the, health of this, parcel is like way higher than this parcel. And then, that you composted in one versus the other, like that could be an indicator of how your regenerative practice is being applied and how it's, changing the health of the landscape. I won't speak on whether or not, that correlation actually exists, because we haven't done any of that work. But for things like that, I think that you could definitely use remote sensing data. Things like animal welfare and other co-benefits that you talked about, we aren't necessarily using remote sensing. Those might be like in situ, whether it's, like having someone go out and do like a field survey or something like that. So.
Great. Thanks, Christoph.
I mean, I guess I continually want to sing your praises, Dorn, for creating an OpenTEAM, because this is the perfect venue to have these sorts of conversations. And great job, science team at Regen Network. Million, including how the open source community thinks collectively about like calibrating remote data. Like building on Rob's question, like linking it back to things that are sort of in service of the outcome that I think everyone on this call wants to see achieved, how you see what you learned from your pilot kind of growing. And maybe that's both a question for Gregory and the science team as well.
You were sort of breaking up a little, Christoph, so I'm not sure I totally understood the fullness of what your question was.
to give a hot take, awesome what you proved in your first pilot. There's a big need to sort of calibrate input data that can leverage remote sensing technologies that will serve the entire industry we're all about. How do you see this pilot kind of informing and growing in the spirit of the OpenTEAM network and helping us all sort of go further together faster?
Yeah, awesome. So, I mean, I'll try to answer that at a high level because I think that's sort of the intention of it. You just sort of like, how does this all fit together, and then maybe see if the science team wants to fill anything in that I miss, or even like share sort of different perspectives. I think, to sort of bring up what Dan is talking about and others, the opportunity here is to create sort of, I think, sort of a system that gets more and more accurate and more precise over time, because we're all training it together so that we're able to provide ground truth data and correlate that with this sort of global coverage of remote sensing, and use that as a very low cost anchor for estimations and claims about ecological health outcomes, right? So I think what we've done is sort of prove that this is sort of that there's lots of still questions, but it's good enough for some people in the market to put confidence in the approach, which doesn't mean that it's perfect, but it serves as sort of this first foundation that I think we can extrapolate. And I think we sort of see a future in which the regional hubs are doing a significant amount of sampling and research and making it possible to extend much lower coverage for high accuracy estimations in the regions that have similar climate and soil type, so that we can actually create, so that can serve as the foundation for whatever sort of marketplace, registry, or certification process is taking place. It may not even end up being like a carbon offset. It could be like a certified outcome in a supply chain, right? But having this sort of public infrastructure for ecological claims and estimations, I think, is what we're really excited to see happening. And it really is only possible within a sort of an environment like OpenTEAM, where we could, for instance, be creating with Dan and other people, the sort of progressive versioning of how we incorporate more and more of the information about how to estimate uncertainty and attach that to different claims in a completely transparent way, so that the marketplace can see that, while at the same time, different hubs are able to provide data and train and then create coverage for farmers and farms in their regions, again, with similar soil types and climate, so that sort of over time, we essentially create a very rigorous, accurate, and precise estimation tool to underpin our both management and claim systems. So hopefully that's kind of what you're going for, Christoph.
Yeah, I mean, it kind of begs a few more questions. Like, I hear machine learning algorithms and the hairs on the back of my neck go up, because I'm like, I don't really know what that means or how that's continuously improving. And so is it us or the machines governing how we're dictating how these protocols evolve?
Yeah, so a machine learning is basically
about
machine learning still needs us to like train. You're essentially training something, and you're saying, you're teaching a correlation. You're saying, this is like the small amount of work I've done in it, is like land classification. So if I've spent a bunch of time in a particular place, like in Ecuador doing agroforestry classification, and I have existing maps and other data sets, I could go and say, oh, that farm, that's bananas. And that farm, that is, that's actually primary forest. And that is yucca. and I know all of those things. Or like I could walk around my neighborhood here and I could say, you know, that's a garden and that's a forest, right? And those get correlated with what you can see, that what the satellite can see. And so the same thing is happening where we're saying, you know, the soil, we went and measured the soil health in this particular place, and it has this particular multispectral frequency, and we're like registering that. And the more and more that you register those things, the more that you can start to calibrate understanding. It's the same kind of pattern recognition that humans go through. Like I go and look at a house plant and I see that it's wilting. And I know through my experience that because it's wilting, it needs water, right? It's the same thing, or it's getting yellow. And I see it with my eyes, it's getting yellow. And I'm like, oh, that means something is taking place. So, I mean, it's not, machine learning isn't, I don't think, anything scary as far as like, we're sort of like vesting any sort of decision-making or control over a process to machines. It's simply over time creating a graph of correlations that gets more and more accurate so that we can sort of like make sense or sense make about what's happening where.
I'd like to add something like very brief. Also, machine learning algorithms, the main value of those is that they allow for creating like very difficult relationships that are non-linear between all the variables, and you can add a lot of variables. So the model could be as complex as you want, and they would detect the patterns if the patterns exist. Otherwise, a human cannot deal with such amount of intercorrelations and nonlinear relationships, I would say. And with time, we can rely maybe on some machine learning algorithms for prediction without needing soil sampling. But I would say you need like at least 10 years of climate and data all correlated with a high accuracy in order to create like a very robust model. So we are far from that. We still need the calibration.
Well, and I think I wanted to sort of highlight that, Gisel, in terms of the OpenTEAM community and the hubs, in terms of helping to provide some of that training data set, right? Both management as well as the soil samples. And I guess I would prompt you with the time we have left to maybe talk a little bit about, again, how your projects fit in as we're building this sort of ag data commons for calibration, how this project may fit in with some of the other initiatives that are working towards some of these same objectives. Again, I feel like this is an opportunity for some of that pre-competitive sort of work that we talk a lot about, is those calibration sets in terms of land cover and use.
Yes, agree. I think one of the big barriers for all this technology not being, properly being spread, I would say, is the lack of geolocated samples and information from, samples. But we need like very high precision in the geolocation. So I would say if we can at least advocate for that being like, a request from now on, that every farm that it's extracting data from their fields is also collecting the geolocation. That coupled with sharing data would allow to not only provide for all the information for assessing the soil for the different projects, but it could also feed all this training and all this knowledge that needs to be developed in order to be using this technology more broadly. I've been always saying that it would be great if there was like a big global experiment with a lot of observatories. The ideal scenario would be to have observatories in different ecoregions with different climates, and have, for the different management practices, farms that could work as observatories. And so we could train images with the same soil types, the same characteristics and management, and provide for that calibration for assessing this organic carbon or other parameters in the farms that are within that region. That would be great.
I think like I think that like the soil samples are really important. You know, the hub farms can be really helpful in providing that data, but then also on like the science and in, you know, kind of development front for these methodologies. Like, I mean, working with Dan and others interested in this field would be great to help, you know, the kind of like academic work, but then also just like the software behind it. Like Regen Network is all about, and OpenTEAM is all about open source collaboration. And I'm starting to upload all the code that has been used to automate these processes, which includes the, you know, machine learning algorithms we're using. And it would be great if people are interested to get more collaboration on that front. I know like Dan Kane's, you know, done things with regression kriging, which is a really valuable tool. And that's something that we would love to dig into, but also, you know, the bandwidth is a little bit limited. So yeah, like I would invite people just to like check out our GitHub and start forking it and working on that front as well. So, and playing around with it and reaching out and asking questions.
Thanks, Sam and Giselle. We also have somebody on an iPhone. I can't tell who that is, but somebody calling in who's got their hand up.
Oh, that's me. Hi, my name is Jeannette. I'm from SIBO Technologies, and great conversation. I just wanted to speak up because my entire PhD background is in digital soil mapping. And so there's an entire robust field called digital soil mapping that has spent the last 20 years pretty much intensely devoted towards using, machine learning, artificial intelligence, and geostatistics like regression kriging to predict soil carbon at scale. And so there's an incredible wealth of literature, and it's still a really robust and active field. And so I highly recommend kind of digging into that stuff. And then from the remote sensing perspective, digital elevation models are one of the best covariates you can ever use to predict soil carbon. So just focusing on satellite imagery will never get you there. But if you start to incorporate different derivatives of elevation models, you can dramatically kind of increase your accuracy, largely because those elevation models relate directly to where water is moving. So great work. It's exciting to see all the progress.
Great. And Jeannette, so pleased you're able to join us today. So I want to, at this point, I would like to hand it back to Laura to talk a little bit about sort of what's coming up next and some of the activities within OpenTEAM to help continue this conversation.
Before you do that, can I just share one sort of parting thought on our end? So I think our sort of larger theory at Regen, and I think this is shared probably broadly in OpenTEAM, but I don't want it to go unspoken, is that we should be as transparent as possible in sharing exactly, how we're making what conclusion about where, and then be rigorous about versioning so that we can just transparently, just like we're doing right now, say, okay, this was our first attempt. This is our first version. It has the following shortcomings that we know of, and it has the following shortcomings that the community has identified. Therefore, the next version that we're doing in this open source iterative way will include the following steps, right? And then we can just keep moving forward in this sort of iterative way and build tools that really are not sort of paralyzed by trying to get it perfect first, but instead can progressively evolve so that we all have access to the kind of sort of information tools that we need to make this all come true, and to know when we're actually making statements about real ecological change, which is what it's all about. Because without that sort of foundation of what intersubjective verification together, it's going to be really hard to know who's saying what, how accurate who's saying something about where is. It's very hard when it's siloed and we're sort of defending reputation instead of sort of like building a knowledge commons together. So really grateful for this conversation and excited to be just like iterating with everybody through this. And yeah, grateful for our awesome science team for for putting all the work in.
Yeah.
And really quick, going along with that, I just shared in the chat a feedback form because we want to open our methodology and just our presentation for any comments that you guys have about the methods or, the presentation or whatever else. So I would invite you to, if you have any feedback on specific sections or just overall your thoughts about this, that would be great as we could work it into our versioning. So.
Yeah.
Awesome.
Thank you so much, Gregory and Sam and Sophia and Giselle and everybody here, and Gregory for framing that. It was well articulated in terms of, why we're here together and how OpenTEAM's, functioning as a community. So really appreciate that.
Yes, and I think to tag off of what Gregory said too about building that knowledge commons, and I think the need for ground truthing, some next steps that are coming up across our community include really engaging our hubs at a higher level. And we're going to be having a series of kind of in focus conversations about things like remote sensing and how the hubs can support the modeling that you want to do and provide the data on the ground that you need. And we know that it's going to be a process, but I think this conversation will really support what hubs can do and how they collect the data that you need to train models. Yeah, I look forward to continuing this conversation. If anyone would like to be involved in the science side of this conversation, please reach out to me. I'll drop my email. Well, everyone should have my email. And I can include you in that conversation. And we'll continue to also update hubs on what is possible and what can support them to have the remote sensing tools that maybe aren't available right now so easily, but could be in a year from now or 2 years from now. So yeah, a constant learning curve for all of us. Anything else to add, Dorn? I see there's a few comments.
Again, I'd just like to express my gratitude for everybody's active participation in this conversation, and so we can all again learn together. And so I appreciate you tuning in both for this in-depth, and we've got some really exciting ones lined up that I think each one sort of builds on some of the last. So again, thank you all, and we'll see you again soon.
Thank you.
Thank you all.
Thanks, Sam, Giselle,
Thanks,
Sophia, Gregory.
Yeah, thanks everyone.
That's awesome.
Later.
Great.
Just what we want to see.